Chapter 6, Thermochemistry. This is a recap of the lesson that was taught before our 2-week break. So I'll go over this a little quickly. Defining energy. Energy is simply the ability to do work. The law of conservation of energy just states that energy is neither created nor destroyed, but simply converted from one form to another. Two kinds of energy we'll be focusing on: potential energy and kinetic energy. If something has potential energy, that means it has the ability, it's a stored energy with the ability to do work. Several types of potential energy: a stretched or compressed spring, if released, then could do work. So therefore that has stored energy or potential energy. A boulder perched on the edge of a cliff has the potential to do work if pushed off. So it has gravitational potential energy. There are two ways to transfer energy: through work, as we just saw with the ball A and ball B, and through heat. Now let's look at the example again that we were looking at a minute ago. In this case, in the second case, ball A also has the same amount of potential energy that it had in this case. But in this case, if ball A rolls, it will probably roll down the hill a little slower, therefore transfer less energy to B than it will in this picture, even though the potential energy of ball A is the same. The difference is the surface. As ball A rolls down, some of its energy will be transferred to heat through friction, because they're obviously, the rougher the surface, the more the friction. So this is an example of the fact that the energy change is independent of the pathway, because in both cases ball A had the same amount of energy and lost the same amount of energy as it fell down the hill. The only difference in the second picture from the first picture is that ball A in the first picture transferred more of its energy to ball B and less of its energy to heat through friction. In the second case, ball A transferred more of its energy to friction, to heat through friction, and less to B, but the total was the same. So the energy change is independent of the pathway. However, work and heat are both dependent on the pathway. So energy is a state function. A state function is defined as a property of the system that depends only on its present state. It does not depend on the past or the future, therefore it's independent of the pathway. The same amount of energy in both pictures, ball A had the same amount of energy, so therefore it's a state function. It lost the same amount of energy as it fell. Work and heat were different in both of the scenes that we saw a minute ago. For instance, this ball, if it rolls down the hill, follows straight down, it will lose the same amount of energy as if it rolls down the hill following this path that I've drawn with the red pen. However, if it takes the second path, it will lose more of its energy due to friction. So more energy will be converted to heat, and less energy will be converted to doing work on ball B. So you see how elevation in this case is a state function, just like potential energy was a state function. But work and heat are not. A few terms as we move further. A system is whatever we're focusing on. You define the system based on what you're interested in and what you're looking at. The surroundings is everything else. A system is exothermic if the heat flows out of the system. If it loses energy, then it's exothermic. That means the system itself is losing heat or energy to the surroundings. If a system is endothermic, that means that the surroundings are losing heat to the system. The key here is the energy gained by the surroundings must be equal to the energy lost by the system. Formula for work again, and think about this in terms of a gas. In order for a gas to do work, it must expand. If a gas contracts, work has to be done on the gas in order for the gas to do that. For an ideal gas, from the point of view of the system, work is defined as negative pressure times change in volume. If you think about the formula for work in mechanical systems, work equals force times distance, and relate that to a gas. Pressure is the force-like quantity for a gas, and change in volume is the distance-like quantity for a gas. We'll talk about the negative sign in just a minute. But first, let's talk about the units of work. Pressure we measure in atmospheres, and volumes of gases we'll measure in liters. So the units here you will get are liter dot atmospheres. Most of the time you'll want this unit in joules because work is measured in joules, energy is measured in joules. So we'll need to convert that using this equality. 1 liter atmosphere is equal to 101.3 joules. Now, why is the negative sign here? For an expanding gas, delta volume, change in volume, is positive because the gas is expanding, therefore the volume of the gas is expanding. That will be a positive quantity because delta V, the change in volume, equals the final volume of the gas minus the initial volume of the gas. If the gas is expanding, this will be bigger, therefore positive. But we want work to be negative because if a gas does work on the surroundings, then work must be negative because the gas is actually losing, in a way, it's actually losing energy when it does work on the system. Now time for an example problem. This is a simple, straightforward problem. Calculate the work associated with a contraction of a gas from 75 liters to 30 liters at a constant 6 atmospheres in liter atmospheres and in joules. So they want this in liter atmospheres and in joules. So our formula for a gas, work on a gas, is equal to negative pressure times the change in volume. So first we'll calculate delta V, and that's equal to V final minus V initial. So it says it went from 75 liters to 30 liters. So 30 liters is our final volume. 75 liters is our initial volume. Therefore, our delta V will be negative 45 liters. So now we're ready to plug this into our equation. It says that our constant pressure is 6 atmospheres. So we'll say negative 6.0 atmospheres times negative 45 liters. And that gives us negative 270 liter atmospheres. There's the answer to the first part. They ask us for this in liter atmospheres and in joules. So now we need to change this to joules. We'll say negative 270 liter atmospheres times 1 liter atmosphere equals 101.3 joules. And that equals negative 27,351 joules. So there's our answer in liter atmospheres and in joules. Thermodynamics is the study of energy and its interconversions. The first law of thermodynamics is simply the law of conservation of energy. Energy is neither created nor destroyed. It simply changes forms. Internal energy. The internal energy of a system, we'll use E to denote that, is the sum of the kinetic and potential energies of all of the particles in the system. Now, to change internal energy, you can change internal energy by doing work on the system or the system doing work, by adding or subtracting heat from the system. So we can write an expression for the change in internal energy is equal to Q, which is just simply heat, plus W, which is work. It's a very simple equation. You just have to make sure that you get the signs of Q and W correct. Now, if delta E is negative, that means the system loses energy. When delta E is positive, the system gains energy. Now Q again stands for heat. Q is negative, that means heat was lost and it's exothermic. When Q is positive, heat is gained, therefore endothermic. Now let's look at this next example. Calculate the energy change of the system if 38.9 joules of work is done by the system with an associated heat loss of 16.2 joules. Well, our equation again, delta E is equal to Q plus W. Now it gives the fact that work is 38.9 joules, but we need to know if that's going to be a positive or a negative. How do we know that? It says work is done by the system. Therefore, if work is done by the system, work is negative. So W equals negative 38.9 joules. And then it says with an associated heat loss of 16.2. So Q, since it's lost, it will be negative 16.2 joules. So the change in internal energy of the system is going to be equal to negative 16.2 joules plus a minus 38.9 joules. Therefore, delta E is equal to negative 55.1 joules. Next example. A piston is compressed from a volume of 8.3 liters to 2.8 liters against a constant pressure of 1.9 atmospheres. In the process, there is heat gained by the system of 350 joules. Calculate the delta E of the system. Again, delta E will be equal to Q plus W. We just need to make sure we get our signs correct. All right, so first we want to find the work. So work is equal to the negative of pressure times the change in volume. Change in volume is equal to V final minus V initial. We'll just put VI there. So first let's find our delta V. Delta V will be equal to 2.8 would be our final volume, and 8.3 is our initial volume. So delta V equals negative 5.5 liters. So now we can calculate work. Our pressure is given as 1.9 atmospheres, so we'll say negative, and then 1.9 atmospheres times negative 5.5 liters will equal positive 10.45 liter atmospheres. There's our work. But since we have it in liter atmospheres, we need to change it to joules, so let's do that. 10.45 liter atmospheres, and that gives us 1,000, and that is our work. Now we just need to decide if this 350 is going to be positive or negative, because it says the heat gained by the system of 350 joules. What does that mean? When heat is gained, it is positive. So our Q will then equal positive 350 joules. So now our change in internal energy is equal to 1408.6 joules. Now let's recap. Thermodynamic quantities consist of two parts, a number and a sign. The number just tells you how much or the magnitude of the change. The sign tells you the direction of the flow. Q represents heat. The sign reflects from the system's point of view. If Q is positive, that means it's endothermic. That means heat was gained by the system. Exothermic, Q is negative, that means heat was lost by the system. Green is the surroundings. If energy is released by the system, then internal energy is less than 0 or negative, exothermic. If energy is gained by the system from the surroundings, then your change in internal energy is greater than 0, therefore endothermic. Greater than 0, positive. Now work recap. Again, the sign reflects the system's point of view. The system does work on the surroundings, then work is negative. You can kind of think of that as the system losing energy. If the surroundings do work on the system, then work is positive. Now let's look at these exercises. Determine the sign of delta E, or the change in internal energy, for each of the following with the listed conditions. Okay, for A, both of these are endothermic processes. So we'll look at, if it's endothermic, what does that mean? That means that heat is positive. As long as it's endothermic, your heat is positive for both of these situations. So in the top situation, it's endothermic. That's how I know that heat is positive. And it says it performs work. Therefore, work is negative. If the system does work on the surroundings, work is negative. So now, both of these are negative and both of these are positive. In the first case, work is greater than heat. The negative is greater than the positive. What will that mean? That will mean it's negative, therefore internal energy is negative. The second case, again, work is negative, heat is positive. So if the negative is less than the positive, then it will be positive. Now let's look at this. Work is done on a gas and the process is exothermic. If work is done on the gas, then that means that work is positive. Both of these cases, work will be positive. And then it says the process is exothermic. That tells us that heat is negative. So in the top case, positive greater than negative, then it will be positive. Change in internal energy will be positive. Second case, work is less than heat and work is positive and heat is negative. Positive less than negative, then it will be negative.